So thus far, we have set up the formalism of quantum mechanics, right? In particular, the last postulate of quantum mechanics, which is the Schrodinger equation, which tells you how states time evolve. It tells you that the time evolve according to the Hamiltonian operator, right? So we've learned how to solve this equation in a very general fashion, and then how to get the time independent Schrodinger equation. And then we have discussed how the equation looks in various representations and so on and so forth. But for all practical purposes, we'll be using the X representation to solve this equation, because as we will quickly demonstrate, to solve at least most one-dimensional potentials, the X representation is the most straightforward and convenient. And this is also true in 3 dimensions. Okay, so before we move on to the study of certain one-dimensional problems, there is one thing that we have not talked about yet, and I'd like to talk about it briefly before we move on to one-dimensional stuff, one-dimensional potentials. And this is the very interesting notion of the existence of different pictures in quantum mechanics to understand the dynamics. Okay, so in particular, today we will talk about the Schrodinger versus the Heisenberg pictures. Okay, so what is this? So let us quickly recap. The Schrodinger picture is what we have been employing thus far. What is the Schrodinger picture? In the Schrodinger picture, the states, the psi of t, right, are time dependent, and the operators like h are time independent, right? So as time changes, the states evolve according to the operators. The operators don't change. That is what our intrinsic understanding of this picture. So in the Schrodinger picture, which I will call SP, right, states are time dependent creatures. Operators are time independent, assuming they don't explicitly depend on time. They don't, time independent here simply means that they don't evolve with respect to time. Okay, so they don't evolve with respect to t. Okay, so that is what time independent in this context means. All right. So there is another picture where this whole thing is switched around, and this switching around can be important to understand certain problems in quantum mechanics. So before we do that, let us quickly ask ourselves, what is it that we want to compute in quantum mechanics, right? Okay, so we have understood how the state evolves with respect to time, and finally, what is the question that you're interested in? The question that we are always interested in is to compute amplitudes, right? So suppose if we have a system in one state, psi I, and it evolves to a final state psi f, what is the probability for this to happen, right? In particular, suppose the state initially, suppose the state is psi I initially and evolves to some final state psi f. What is the probability? Okay, or in particular, what is the amplitude? What is the amplitude for psi I to evolve to psi f? Well, the amplitude for this to happen, as you clearly know, is the overlap of psi I and psi f. So the amplitude for this is basically psi f, psi I, and the probability for this to happen is the absolute square of the amplitude. So this is something that you already know. Okay. Now let us, for instance, assume that this final state psi f has been achieved from psi I by the action of some Hermitian operator A. Okay. In particular, let us assume that psi f equals A psi I. We don't have to assume this. I'm just doing it for simplicity's sake. So what I'm basically saying is psi f psi I, the amplitude, is basically now psi I A psi F. Okay. So this is the stuff that we are interested in quantum mechanics. This is the stuff that we want to compute all the time in quantum mechanics. What is the probability of transition in hydrogen atom from one state to other is exactly this question. Right? So that is, all of physics is based on dynamics. So dynamics has to do with the amplitudes and probabilities for things to change. If nothing changes, then the world would be very boring. Okay. So let us try to evaluate this formally in the Schrodinger picture. So what do I mean by that? Notice that even though we did a very roundabout way of solving the Schrodinger equation, which is the practically correct way of solving the Schrodinger equation, there is actually a formal solution to the Schrodinger equation that I have written above, the time-dependent Schrodinger equation. After all, this is just a very simple differential equation, first order differential equation. I should be able to integrate this very easily. So IH bar d psi dt equals h psi. Okay, as you can easily see, this can be integrated. So d psi over psi equals h over IH bar acting on psi, which is minus IH over h bar acting on psi. Forgive me. So this is dt, right? Which can be trivially integrated to give me psi is e to the minus IHT over h bar acting on psi of 0. The integration constant, obviously, if you evaluated at t equal to 0, would give you the state at time t equal to 0. So I will rewrite the left hand side so the time dependence is explicit. So psi of t equals minus e to the minus IHT over h bar psi of 0. Okay. So this is actually the formal solution of the time dependent Schrodinger equation. So if the solution is so straightforward, why did we not do this the first time we introduced Schrodinger equation? Well, because for most practical purposes, it is useless. Because as you can clearly see on the right-hand side, e to the minus IH, where the h is an operator, is a sum of the Hamiltonian of all powers. So unless you have very special situations in which this e to the minus IHT over h bar can be evaluated in a very straightforward fashion, this formal solution doesn't really help us in all practical problems. And doing it the way we initially did it, by using time independent Schrodinger equation and then plugging it, writing down the most general solution, is a more straightforward way of solving the Schrodinger equation. Of course, there is nothing wrong with this solution. In fact, we will actually, when we deal with time-dependent perturbation theory, we will take recourse to this particular equation. It has it's very useful. But for now, let us simply recognize that this is the formal solution of the time-dependent Schrodinger equation. Okay. Please stop me if you have not seen this before, and if you have any questions. Notice that it is not just a number acting on a ket; it is an operator Hamiltonian acting on ket. So this has to be understood as the operator. Let us say k equal to 0 to infinity minus I h to the n, sorry, minus I t over h bar to the n 1 over n factorial. This operator acting on the state psi of 0. Okay, that is how you have to understand this equation. Okay, so there is an infinite sum here. This is the formal solution at least. Anyway, so let me plug in this formal solution in my equation for amplitude, which I will call equation 1. So I'll plug in equation 2 in equation 1. Okay, and I'll actually make one modification. Since I'm dealing with what I'm calling the Schrodinger picture, I will call all these kets with a subscript s, where s stands for Schrodinger. Okay, and the operators also I'll put in with the subscript s. So if I substitute equation 2 in equation 1, what do I get? The amplitude for a state to go from an initial state psi I to a final state psi f through the action of some Hermitian operator A is given by, the bra psi f is given by, so psi 0 Schrodinger e to the plus IHT over h bar, since this is the bra. A, since this is Schrodinger picture, I will again put AS e to the minus I h t over h bar. Okay. Yes. Okay. Are there any questions about this? I've substituted equation 2, which is a formal solution. Remember that this amplitude is also a time dependent quantity because these states are time dependent quantities.
Hello, sir.
Okay. Yes, question?
Yes, sir. I have a doubt, sir. This psi naught, sir, which is the ket vector at some initial time, will that always necessarily be an eigenket of Hamiltonian operator, or could it be something else, sir?
The ket psi, the question is, will the ket psi always be the eigenvalue, eigenstate of the Hamiltonian operator? Is that the question?
Yes, sir. Yes, sir.
Yes. So if the initial state psi, see, the whole point is that psi time evolves according to the Hamiltonian. So this statement, the first equation that I've written down, the time dependent Schrodinger equation, is a postulate that is always true if psi is the state vector for some particular system, then psi always time evolves according to this particular equation, which means I can always piece up this equation into a time independent part and a time dependent part. Okay, the time dependent part I can always integrate very easily, as we have already demonstrated, and the time independent part is basically the eigenvalue equation for the Hamiltonian operator, right? So if this equation is always true, and if psi is the state vector of the system, then the x dependent part, psi of x, this h acting on in the position representation, this is the time independent Schrodinger equation, right? If this is true, if this equation is true, then this equation is always true, assuming that psi is the state vector of the system. Okay, so at all points in time, the state vector itself is different, but assuming that the state vector time dependence is determined by the time dependent Schrodinger equation, you can always write down a corresponding time independent Schrodinger equation, which tells you that the corresponding spatial part of the wave function is always the eigenfunction of the Hamiltonian operator. Make sense?
Yes, sir. Yes.
Any other questions? Okay, so let's recap. In the Schrodinger picture, the states time evolve, the operators are just standing there doing nothing, right? Well, they just act on the states, but they themselves don't change with respect to time. But suppose if I define a new ket, instead of the Schrodinger kets, I'm going to define a new ket, and I'm going to call this psi with a subscript of h. And this ket is related to the Schrodinger ket via the relation e to the I h t over h bar psi t Schrodinger. Okay. So I'm not doing anything very drastic. I'm simply saying that I'm going to do quantum mechanics with a different set of kets. I'm not interested in the Schrodinger kets. I'm going to be looking at what are called Heisenberg kets. Okay. Now, why do you want to do this? Well, you want to do this because this achieves something profound. Notice that this is equal to I h t over h bar. Remember that Schrodinger kets time evolve according to equation number 2. So substitute equation number 2 over here, minus I h t over h bar psi 0. So you can formally identify the Heisenberg ket with the Schrodinger ket at time t equal to 0. And the Schrodinger ket at time t equal to 0 is actually time independent. It is just one particular ket at one particular value. Sachin is asking, should there be a psi 0s? Sorry, where exactly? I'm not getting you. So if you can point out where, I can look at it. Okay, so for now, simply understand that if I simply relate the Schrodinger kets and the Heisenberg kets via the relation, which I will call equation number 3, then by definition, the Heisenberg kets are time independent. So psi h is time independent, which means at every point in the evolution, I can either look at the Schrodinger ket, which is an explicit function of time via equation 2, or I can describe the system using Heisenberg ket, which is a time independent quantity. Okay. Now, this might raise an important question, a rather confusing question. If I want to describe my quantum mechanics, dynamics and quantum mechanics using the Heisenberg picture, then where is the time dependence? Well, let's again look at the amplitude. So for a system to go from an initial state to the final state, psi f, psi I, okay, so I'm looking at this particular equation. I can identify, so let me again go back to equation number 1, okay. If I go back to equation number 1, then this is basically saying that the amplitude is the overlap of two Schrodinger kits, which I can write as psi I a psi f. So I'm simply going to substitute, sorry, wrong color. I'm simply going to substitute everything here blindly. What am I going to get? This is equal to, if I simply recognize that psi 0 e to the iht over h bar is simply my Heisenberg kit multiplied by e to the iht over h bar. So remember that if you look at this equation, this part is just the Heisenberg kit, and this is some operator. Again, so the Schrodinger kit at time t equal to 0 is the Heisenberg kit, and this is some other operator. So I'll retain the operator and write everything in terms of the Heisenberg picture. So this can be written as psi h e to the iht over h bar as e to the minus iht over h bar psi h. Okay. So Niyati is asking, psi 0 is dependent on time, right? So how is psi h independent of it? No, remember that the t, so this psi 0 is psi evaluated at time t equal to 0. So there is a t right there. So you might be tempted to think, as you correctly point out, that this is a time dependent kit. But remember, when I say time dependent, I simply mean that as time evolves, the state changes. Okay, that is not what is happening here. The Heisenberg kit is frozen in time at time t equal to 0. So even though there is a t equal to 0 there, that is simply a label to tell you what kit it is. Okay. So as time evolves, the Heisenberg kit simply still remains psi 0 at time t equal to 0. So as t goes from 0 seconds to 25 seconds, the Heisenberg kit is still psi 0 at s. Okay, it doesn't time evolve. So yes, you're right, there is a t equal to 0 implicit there, but that is simply a label to keep track of at what time are we evaluating this. So now let us get back to the question of where is the time dependence. Well, now I can take all the time dependence from the operators wherein I had these factors of e to the iht over h bar and simply redefine my operators as being time dependent. So I can look at this combination and I will claim that my operators in the Heisenberg picture time evolve according to this very complicated looking formula. So if I identify the operator in the Heisenberg picture to be related to the Schrodinger picture via the relation and if I relate the kit in the Heisenberg picture to be related to the Schrodinger kit via the relation if I do this, then notice that my amplitude doesn't change. It is the exact same amplitude, and my amplitude should not change because amplitude is an experimentally determined quantity. So whether I look upon this amplitude psi f, psi I in terms of the Schrodinger picture or the Heisenberg picture, I will get the exact same answer. If this is 3, it will be 3 in the Schrodinger picture or the Heisenberg picture. But the difference is here the state depends on time, the operator is time independent, and here the state is time independent, whereas the operator is explicitly time dependent. Okay, so it is so the amplitude is
Sir,
yes,
sir,
somebody.
in the identity that you wrote, can
Ah,
you go to the student? There is psi t of Schrodinger. Psi of t.
psi of t of Schrodinger. Where did I? Sorry,
In the second identity.
this one.
Is psi of Heisenberg is equal to e raised to iota h cut t by h bar t by h divided by sorry into psi of 0. Instead of 0, shouldn't there be psi of t?
Oh yeah, you're absolutely right. Thank you. Thank you. Correct. And this is formally equal to simply psi 0 of s. Yes, thank you. Any other questions or comments? Any other mistakes I made? Okay. So the next semester, we will actually see another picture in which I can do quantum mechanics called the interaction picture, which is sort of midway between the Schrodinger and the Heisenberg pictures. But I don't want to confuse you by introducing that now. But the whole point of this is to tell you that there are situations in which things would be slightly easier when you look at it in one picture as opposed to the other. Okay. Now, in the solution of most one-dimensional problems and things like that, we mostly don't take recourse to the Heisenberg picture, even though I will give you a tutorial problem in which this is explicit. Simply because all potentials are simply functions of x, and it is much more straightforward to simply solve for the time explicit time dependence of the state vector and take recourse to the Schrodinger picture. But that is not to say that there are not situations in which the Heisenberg picture is useful, and we will see a couple of examples in the tutorial that we will see. Okay, so for now, please understand that one can equivalently do quantum mechanics using two different kinds of pictures of time evolution. One picture in which the states are frozen with respect to time and the operators change as time evolves. This is the Heisenberg picture. The other picture in which the operators are frozen with respect to time and the states time evolve, and this is the Schrodinger picture. Okay? And the calculation of amplitudes in both these pictures, as we have demonstrated, is exactly the same whether you calculate amplitudes using the Schrodinger picture or the Heisenberg picture. Nothing will change. The amplitude, the result of the amplitude would be the exact same thing in both the pictures. Okay. So this was a sort of a note that I wanted to point out because this will be more relevant in subsequent discussions, particularly in the next semester. But for now, let us get back to our study of solving the Schrodinger equation. Okay. So we want to understand, before we move on to complicated three-dimensional problems, we want to understand the Schrodinger equation and simple one-dimensional problems. And as usual, this is misbehaving, so I'll stop share and share again. Any questions up till now? Okay. All right. So let us leave out this. So we want to know how to solve the Schrodinger equation for some basic one-dimensional problems. So let us move on to the study of 1D problems. And I realized that most of you or all of you would have studied a bit of quantum mechanics in your BSc, and you have learned how to solve certain simple potentials like the box potential and harmonic oscillator potentials and things like that. Though I will talk about the harmonic oscillator in detail using the creation and annihilation operators, I will leave out some simple problems like the box potential and things like that in this course. This will be relegated to either some problem set or tutorial. What I will try to concentrate on are things that you might not have seen in your BSc. But before we do that, let us sort of try to understand some general features of potentials, one-dimensional potentials in quantum mechanics. Okay. So let me draw a picture. So this is my y-axis, my x-axis. So this is some kind of a potential that I think this is from your book by Zetili, which I think discusses this nicely. Okay. So what is this? This is some kind of a potential. I don't know what potential this is, but this is some V of x. Okay. My V of x has a very well, strange looking dip right here. So I will call this x is equal to 0. I can always reorient my x-axis so that the minimum happens at x is equal to 0. And this is asymptotic. So the asymptotic value here is some value of the potential. Let us call this V2. Okay, and this is flattening out at some other point, and let's call this V1. And this is the point at which the potential is the lowest value. Let us call this Vmin. Okay. All right. So we want to understand what happens if a particle that is moving along the x-axis, this is my x-axis, experiences this potential. So first, let us try to understand what happens classically. Okay. So let us see what happens if I have a particle that I'm throwing into this potential field, into this force field, and this particle has some energy. I'm giving it some kinetic energy initially, and let us say that this kinetic energy is some value between, let us say, the minimum of the potential and V1. Okay, so let us say that case 1, my energy of the particle that I'm throwing into this potential has a value between Vmin and V1. Okay, what will happen? So let us say that this is my energy. Let us call this E1 just to be consistent. Now, what do you expect will happen classically? Well, the particle can at most go from this point, which I will label as some x1, and go to this point, which I will label as x2. Now, when the particle reaches the point x2, it cannot go up further, right? This motion would be restricted because classically, excuse me, the particle just doesn't have enough energy to overcome the potential barrier, right? So think of this as jumping over a wall. If you don't have enough energy to scale the wall, then there is no way you'd be able to get to the other side. So when the classical particle reaches the point x2, the most it can do is trace back and go back to the point x1. Now, when it reaches x1, it again cannot go back up because it doesn't have enough energy to scale the potential wall. So the most it can do is go back to x2. And it sees x2 and it has enough energy to go from x1 to x2 because the potential is lower than its energy. But once it reaches x2, again, all it can do is sadly come back to x1. So all it can do classically is execute some kind of a motion that goes back and forth between x1 and x2. So x1 and x2, for this reason, are called the classical turning points. Classical turning points. Okay. So classically, I can make the statement that the particle can only be found between the points x1 and x2 if I give it energy such that it is greater than the minimum value of the potential, but less than some other value, which I will call V1 for this particular potential that I've drawn. Is this logical picture clear to everybody? Are there any questions? Okay. So then what does the picture look like in quantum mechanics? Suppose if the picture is quantum mechanical, and if I have a quantum mechanical particle that is coming in with energy E1 and it sees its potential, again, the potential is the same whatever you do. So it has some minimum value Vmin and it has some V1 at which it asymptotes. And then it keeps increasing along the positive x-axis till it reaches the value V2 and it asymptotes at that particular. So my particle has energy E1. So corresponding to the classical turning points, remember the classical turning points simply means in classical mechanics that the particle can only be found between these 2 points. So if I go beyond this point, the particle cannot be found. It is just not there. The corresponding picture in quantum mechanics is one of what are called bound states. Bound simply means, just like the classical picture states, again I will stop share and reshare. Sorry. So bound simply means that the particle is basically constrained within some specific region of space. Okay. Excuse me. All right. So, but I cannot in quantum mechanics simply claim that the particle cannot be found beyond x2 or cannot be found beyond x1. I will not make such claims, and I'll tell you why we cannot make such claims as we move forward in this course. But what I can basically tell you is that for such states in quantum mechanics, if I go far enough in x on either side, I should not be able to find the particle in quantum mechanics also. In other words, I'm looking for solutions of the Schrodinger equation such that the wave function goes to 0 as x goes to plus minus infinity. Okay. An example would be the box potential that I'm sure many of you have seen. In the box potential, what you basically have is, this is your x-axis. You have a potential such that the potential is infinite between some, let us say, minus a to plus a. So the potential is infinite at x is equal to minus a and x is equal to plus a, and the potential is 0 inside. Okay. In this case, I can be sure that the particle, the wave function for the particle should be psi of x should be equal to 0 beyond x is equal to plus minus a. Because there is an infinite potential on this side and this side, there is an infinite force, obviously. So the particle cannot be found beyond the points minus a and plus a. So even in quantum mechanics, the picture that emerges is that the particle is sort of bound between two values of x. Classically, the particle cannot move upwards, but it can still move downwards, right? Niyati is asking, yes, the particle can certainly move downward. In fact, that is how it executes the oscillation, right? So assume that this is some kind of a harmonic oscillator potential. Okay, so for any very small region of space, I can assume every potential looks sort of simple harmonic, right? If I expand around the minimum. So when it reaches x2, it can roll down the hill, right? So it's, if you assume that this is a ball and this ball is rolling down this hill, right? Like this. So it can move downwards and reach all the way here. And when it reaches here, it cannot move upwards classically. It again moves down and rolls down the hill again and reaches the point x2 again. And it keeps rolling back and forth this hill, right? So yes, you're certainly right. It cannot move upwards, but it can still move downwards. I'm not saying the particle is not moving at all classically. I'm simply saying that the particle cannot be found beyond x1 and x2. It is simply oscillating between x1 and x2. That is why they are called turning points. Okay. So this is an example of a bound state in quantum mechanics. Notice that the potential doesn't have to be infinity. Okay. So even if I change this picture slightly and and assume that the picture is such that I will erase this infinite lines, and let us say that it is somewhat like this. Okay. Now, even this potential will admit bound states. It can also admit what are called scattering states. We will see that later. But notice that if I shoot a particle with some energy that is less than this, let us call this energy some V0, less than this V0, then obviously if the particle is inside the potential, it will be stuck inside the potential. Okay, it cannot come outside the potential. Of course, that is classically. Quantum mechanically, we will find that for this particular case, if the potential is not infinity but is a finite height, there is a finite probability for the particle to escape quantum mechanically. That is called tunneling. We'll come to that question later. But even for this case, for example, psi of x would still be equal to 0 if I try to find the particle at x is equal to plus minus infinity. So let's write it differently. So even for this, psi of x would go to 0 as x goes to plus minus infinity. Of course, psi of x will not be 0 at x is equal to, let's say, plus a plus 0.2 or something like that. There I would have a non-zero wave function because of tunneling amplitude, which we will talk about later. But as I go sufficiently far away in x, then for bound state systems, I would have the wave function going down to 0. This is the quantum mechanical equivalent of claiming that for a specific for the corresponding classical problem, if there are classical turning points, then the particle cannot be found outside the classical turning points. In quantum mechanics, this statement is strictly not true. I cannot claim that the wave function is always 0 outside the classical turning points. If I have an infinite potential like the box potential, then of course it will be 0. But for any finite potential, I cannot claim that the wave function will be exactly equal to 0 outside the classical turning points. But if I go sufficiently far away from the classical turning points, particularly as x goes to plus minus infinity, I can be sure that for bound states, there is 0 probability of finding the particle so far away. If the particle is stuck inside the potential, it can leak to some extent beyond the potential, but it cannot go all the way to x is equal to plus minus infinity. So bound states are characterized by a demand on the wave function that psi of x goes to 0 as x goes to plus minus infinity. Okay, which means bound states are clearly normalizable states. So we can work with bound states. Remember that normalizable states are those that don't blow up as I go to x is equal to plus minus infinity. They have finite norm. So these are clearly normalizable states and well-behaved states that one can use, for example, as basis functions and things like that. So all the mathematical tools that we have developed clearly applies to bound states. Okay. So there is another case that we can investigate. So let us say that for the same potential, I'm throwing the particle into this potential, but with an energy that is, let us say, greater than V1. Okay, so suppose if the energy of the particle is between V1 and V2, let us say, then what will happen? This is an interesting question, right? So remember that if let us say that the energy of the particle, let us call this E2. So let us say that this is my E2. Now, classically, what do you expect? If the particle is traveling in the right-hand side, along the right-hand side, then it will go till it reaches this particular point. Let us call this X3. Now, clearly, the particle cannot go up along this potential and escape this potential classically because it simply doesn't have enough energy. So if it has an energy E2 and is traveling along in the right-hand side, it will simply hit the point X3 and come back. So X3 is again a classical turning point. So for this particular case, X3 is a classical turning point. But now, when the particle comes back, notice that the minimum of the potential on the left-hand side is much lower than its energy. So there is nothing stopping the particle on the left-hand side. So remember in the first case, the particle has a turning point on the right and a turning point on the left. But in this particular case, as the particle comes back, it sees no obstruction because it has a lot of energy, much more than the value of the potential at all points along the negative x-axis. So it will just keep going merrily along its way. There is nothing stopping the particle. So the motion of the particle is bound on one side by the classical turning point, but it is unbound on the other side. So this is a kind of an interesting motion where the particle has a classical turning point on one direction, but has no turning point in the other direction. And on the other direction, where it simply keeps going on and on and on, such states in quantum mechanics are called scattering states. Scattering states are those states for which, as x goes to plus minus infinity, the solution still exists. So psi of x does not go to 0 as x goes to plus minus infinity, simply because there is nothing stopping the particle from moving anywhere it wants. Okay. So this is an example of a scattering state. So there is two kinds of solutions possible in quantum mechanics. Bound states, which are corresponding to the classical picture of having two classical turning points, and scattering states where the motion of the particle is basically unbounded. For example, a free particle solution is what is called a scattering state. I mean, scattering states, since the wave function does not go to 0 as x goes to plus minus infinity, scattering states are sort of tricky. They are not normalizable states. Okay. Now, we don't have to be disheartened by this observation because we know what to do with states that are not normalizable. We already saw it in the free particle case. If we have a wave function like e to the ikx, which itself is not a physical wave function, we can still create a physical wave function out of it by adding a whole bunch of different states with different k values together. Right? We introduce the notion of linear superposition and create a wave packet. So we can still understand scattering states in quantum mechanics by creating wave packets and making the wave packets travel. We will make this problem much more precise in the next semester when I talk about scattering in quantum mechanics. I will deal with scattering in this semester in a less sophisticated fashion. Okay. But remember that scattering states technically are non-normalizable states, and we have to be careful in dealing with scattering states. So there is two kinds of motion in quantum mechanics that is possible. One is called a bound state problem. The other is called a scattering state problem. So in a bound state problem, typically you have boundary conditions. So in bound state solutions, a scattering state, I will write down psi of x does not vanish as x goes to plus minus infinity, typically. Okay. Now, I can also identify other scattering solutions in this particular potential. Give me 1 second, sorry again. Okay. So suppose if for this particular potential, I'm throwing some particle with energy E greater than V2, for example, case 3. Let us say E3 greater than V2. Then this particle will never have even a single classical turning point, because if I throw it along the right or along the left, since its energy is much greater than the value of the potential at any point along the x-axis, it will simply keep going along the plus x-axis or minus x-axis, depending on which way it is released. So this is a purely scattering state, and there is no bound states in this particular case for the potential that I have drawn. Only scattering. Okay. So remember that when you study general one-dimensional problems in quantum mechanics, it is possible that you have a potential that admits only bound states, you have a potential that admits only scattering states, or in general you have a potential that admits both bound states and scattering states, like we have just discussed. For example, hydrogen atom would have bound states for low values of the principal quantum number, and when we go sufficiently high, you will have what are called ionization regime, which we will come to when we study three-dimensional problems. Okay, so let me get the chat window up again. Okay, Okay. So there is 2 points about bound states that are very important. The first point about bound states is that they have a discrete energy spectrum. So let us try to understand logically why they should have a discrete energy spectrum. Let us look at this particular potential, for example. Now, if I have to solve this system, I'll have to solve the Schrodinger equation. The way I will solve the Schrodinger equation is I will divide this potential up into 3 regions. Region 1 in which there is no potential, region 2 in which the potential is a constant, which is V0, and region 3 in which there is no potential, right? So Schrodinger equation will give me a solution psi 1 in region 1, psi 2 in region 2, and psi 3 in region 3. Now, the way I would solve it is by saying that my solution on the region 2 and region 3 should both match at x is equal to plus a, because I want psi to be a continuous function. Similarly, the solution at region 1 and region 2 should match at x is equal to minus a for the exact same reason. So you have what are called boundary conditions imposed on the system when you have bound state systems. And you always have more boundary conditions than the number of constants available. So the constants like, for example, the e to the ikx, the momentum or energy equivalent dE, cannot have any particular value, because in general, you cannot satisfy these boundary conditions for any value of energy. Only some values of energy would satisfy these boundary conditions. So the existence of these boundary conditions in bound state problems ensures that the energy or the momentum equivalently can only be certain values. Okay. So whenever you have energy or momentum to be only certain values, you say that the system's energy is quantized in some sense. So my computer is misbehaving too much today. I'll again have to reshare. Sorry about that. Okay. There is no such constraint in scattering states. Scattering states can have any energy they want. The second important point, which I think I've given as a tutorial problem, is that bound states in one dimensions are non-degenerate. This means that two wave functions psi 1 and psi 2 cannot correspond to the same energy E. Okay. If you have not proved this, I will take some time to prove it in the next lecture, because it's a very important point. If you have, then pat yourself on the back. It's a very good proof. This is actually true only in one dimension. We can easily demonstrate that in 2 or 3 dimensions, there can exist degeneracy, even in a very simple harmonic oscillator problem, for example. Okay. So this is a curious case of one-dimensional potentials, that in one dimension, bound states are necessarily non-degenerate. There cannot be two energy eigenstates that correspond to the same energy eigenvalue E. Okay. So if I forget to do this, remind me to prove this in the next lecture tomorrow. So the study of general one-dimensional potentials, which we will go on to specific examples, shows some very nice features in quantum mechanics. Potentials can allow for either bound states or scattering states, depending on certain conditions. And in general, potentials can allow for both bound states and scattering states also. Bound states are normalizable states, scattering states are not normalizable states. We will explicitly work with scattering states when we develop the whole theory of scattering in quantum mechanics in the next semester. It is a very involved subject, so I cannot do it full justice this semester. So we'll study scattering very properly in the next semester. But for now, we will concentrate on bound state problems a little more, and we will talk about certain simple one-dimensional cases, and then we will move on to three-dimensional cases. And I will typically like to finish hydrogen atom, and if time permits, I'd also like to do time-independent perturbation theory. But let us see how far we progress this semester. So I'll stop for now, and please ask me if there is any questions.